Hello dear friends, greetings of the day. In today's video session, we'll be discussing on a special case of problems in design of machine elements where we'll be trying to solve and determine the static stresses developed in the structures. A 50 mm diameter steel rod supports a 9 kN load, and in addition it is also subjected to a torsional moment of 100 Nm as shown in the figure. Determine the maximum tensile and maximum shear stress. Now in this example there is a rod of 50 mm diameter. This rod is subjected to a load of 9000 newtons, and also there is a torsional moment of 100 Nm applied onto this rod. Since the load is away from the axis, there is an eccentricity of 28 mm. So in this case there will be eccentric loading also, means there will be an axial load, there will be a bending load, as well as there will be a torsional moment. Let us start solving this problem by writing the given data. A load of 9 kilonewtons has been applied, which is equal to 9000 newtons. The diameter of the rod is 50 mm. The torque is 100 Newton meter, which is equal to 100 into 10 power 3 Newton mm. This entire component is subjected to three different types of stresses: axial, bending, as well as torsion. Axial, because there is extension of the rod because of this load 9000 newtons. Since the load is placed away from the axis and there is an eccentricity, there is a bending stress, and the torque is applied, therefore the torsional stress is applied on the structure. The equations for this combined loading is given by sigma maximum is equal to sigma AB by 2 plus root of sigma AB by 2 whole square plus tau square. This is the maximum principal stress. The maximum shear stress is given by root of sigma AB by 2 whole square plus tau square. This is the maximum shear stress. And sigma AB can be determined by using the equation sigma A plus sigma B. These equations are used to determine the combination or combined stresses. Let us now start finding the individual stresses like axial stress, bending stress, as well as torsional stress, and use these values in this combined loading equations. So axial stress can be determined by using the formula sigma A is equal to F by A, where A is the area given by pi d square by 4. Therefore, sigma A is equal to F by pi d square by 4. By substituting the values of F and diameter into this equation sigma A, will be able to determine the value for the axial stress, which happens to be 4.583 megapascals. Also, we can determine the bending stresses by using the equation sigma B is equal to mb by z, where z can be given by the equation pi d cube by 32, which is obtained from table 2.7 from data handbook, and mb can be obtained by multiplying the force with eccentricity. In this case, force is 9000 newtons and eccentricity is 28 mm. By substituting all these values in equation for sigma b, force into eccentricity divided by the value of z, will be able to determine the value of bending stress, which is equal to 20.534 megapascals. Let us find torsional stress by using the equation tau is equal to mt by z naught. Here z naught is polar section modulus, which is given by the equation pi d cube by 16, and mt is the torque which is applied on the component, and it is already given in the numerical. By substituting these values, we will be able to determine the value of torsional shear stress, which is equal to 4.074 megapascals. So by calculating the individual axial, bending and torsional stress, we can substitute these values to determine the further combined stresses. Let us now determine the combination of axial and bending. Since it happens to be the normal stress, let us determine sigma AB value. Sigma AB is given by sigma A plus sigma B, where sigma A is 4.583 megapascals and sigma B is 20.534 megapascals. Therefore, we will have the value of sigma AB as 25.117 megapascals. Once we have determined this axial and bending, this value of sigma AB will be substituted in maximum tensile stress formula. Sigma AB by 2 plus root of sigma AB by 2 whole square plus tau square gives the value of maximum tensile stress. By substituting the values of sigma AB and the shear stress which we have already determined, we will be trying to find the value of sigma maximum. And also by substituting these values in maximum shear stress equation, we will be trying to determine the value of tau maximum which happens to be 13.202 megapascals. So that is how we will be trying to find the maximum tensile stress and maximum shear stress in this numerical. Let us now see one more numerical. A steel member is loaded as shown in the figure. So the figure on the right side he has clearly given there is a rod. Determine the magnitude of maximum tensile stress, maximum compressive stress and maximum shear stress. So if you can clearly observe the diagram, it is clearly seen that there is three circular rods which are connected as shown in this figure. One of the circular rod is having a diameter of 100 mm and other circular rod is having a diameter of 50 mm and third bottom one is also having a diameter of 100 mm. A load of 9000 is applied exactly at the center of 100 mm diameter rod, and also it is almost next to 50 mm diameter rod. So a load is applied here. At the same time, a twisting moment of 100 Newton meter is applied on the structure, which is shown in this diagram. The diameters of the rods happens to be 100 mm, 50 mm as well as 100 mm. Now, this rod is subjected to axial stress because of FA and also subjected to torque because of MT. But if you can carefully observe, the maximum stress can be obtained only at the smaller diameter cross section, that is at 50 mm diameter cross section. Since the load applied is away from the axis of 50 mm diameter cross section, there is the chances of bending stress due to eccentricity. So if you clearly observe, there is a eccentricity of 25 mm in the structure. Therefore, this structure has the combination of all the three loads, that is the bending load because of eccentricity, second one axial load, and third one is torque or torsional load. And the main focus will be on a smaller cross section, that is 50 mm diameter. The maximum stress is induced at the section having smallest diameter. Let us write the given data. The diameter D is taken as 50 mm. We will never consider the diameter of 100 mm because the main focus is on 50 mm diameter. The load applied FA is 9000 newtons. It is the axial load, and the torque applied is 100 Newton meter. So 100 into 10 power of 3 Newton mm. The bending load is also same as the axial load 9000 newtons. So this problem belongs to the combination of all the three loads: axial, bending and torsion. So therefore, the maximum stress can be obtained by using the equation sigma AB by 2 plus root of sigma AB by 2 whole square plus tau square. And the minimum stress can be obtained by using the equation sigma minimum is equal to sigma AB by 2 minus root of sigma AB by 2 whole square plus tau square. And the maximum shear stress is determined by using this equation root of sigma AB by 2 whole square plus tau square. Sigma AB can be determined by adding sigma A and sigma B. The axial stress can be determined by using the formula sigma A is equal to F by A, where A is pi d square by 4. Once again, I would like to remind you that it is the diameter, the smallest diameter which we need to consider, that is 50 mm. Therefore, sigma A is equal to F by pi d square by 4. By substituting all the values of F and diameter D, we will be able to determine the value of sigma A, which happens to be 4.583 megapascals. Let us now examine what happens at the inner layer of the cross section and outer layer. Now in this case, the layer which is next to the load is considered as inner layer, which is written on the screen as I, and the layer which is away from the load is considered as the outer layer. So in this structure, the inner layer, especially in case of axial loading, inner layer is also getting extended and outer layer is also getting extended, because of which the axial stress will be tensile at inner layer as well as tensile at outer layer. Now let us determine the bending stress. The bending stress can be determined by using the equation sigma B is equal to mb by z. Z is given by the equation pi d cube by 32, where d is equal to 50 mm. So mb can be determined by using the equation force into eccentricity. By substituting all these values and the eccentricity value of 25 mm, which is nothing but the diameter of the small rod, this diameter 25 mm, and substituting the value of diameter as 50 mm, we will be trying to determine the stress in case of eccentric loading. The bending stress on further simplification will be equal to 18.334 megapascals. This bending stress will be at two different layers, as I have mentioned, inner layer as well as at outer layer. At inner layer, since the inner load is applied in this direction, the inner layer will try to bend and it will try to extend. The outer layer will get compressed. Therefore, the bending stress will be tensile in nature at inner layer and it will be compressive in nature at outer layer. So sigma B is equal to 18.334 megapascals, which happens to be tensile at inner layer, and sigma B is equal to 18.334 megapascals, which happens to be compressive at outer layer. Let us now determine the torsional stress. The torsional stress can be determined by using the equation tau is equal to mt by z naught, where mt is the torque and z naught is the polar section modulus. Polar section modulus is given by the equation z naught is equal to pi d cube by 16, and mt is already given in the numerical as 100 into 10 power of 3 Newton mm. By substituting the values of diameter d as 50 mm and the value of torque, we will be able to determine the value of torsional stress, which happens to be 4.074 megapascals. After determining the values of axial, bending as well as torsional stress, let us also now determine the combined axial plus bending stress, the values whose value happens to be equal to sigma AB. So axial plus bending will be determined at inner layer as well as at outer layer. At inner layer, since both are positive, that is both are tensile in nature, we are going to add sigma A and sigma B. Therefore, sigma AB is equal to 4.583 plus 18.334, which will be equal to 22.917 megapascals, which is tensile in nature. At outer layer, sigma AB will be equal to sigma A minus sigma B, because at outer layer only axial stress is tensile and bending stress is compressive. Therefore, sigma AB is equal to 4.583 megapascals minus 18.334 megapascals, which happens to be compressive with the value of minus 13.751 megapascals. So we have determined the stress at inner layer as well as outer layer. Now by using this values of sigma AB and tau, we will now determine the maximum tensile stress and maximum compressive stress as well as maximum shear stress. At inner layer as well as outer layer, we will be trying to determine the values of principal stresses as well as shear stress. At inner layer, the maximum normal stress can be obtained using the following formula. By substituting the values of sigma AB and tau, which we have obtained, we will be having the value of sigma maximum to be 23.646 megapascals. Since the value is positive, it is understood that the sigma maximum is tensile in nature. At the same time, the minimum normal stress can be obtained by using the following equation. After substituting the values, we will be getting the value of sigma minimum as minus 0.703 megapascals. Also, the maximum shear stress at inner layer is determined by using the formula tau maximum is equal to root of sigma AB by 2 whole square plus tau square. The value of tau maximum is 12.161 megapascals. The similar formulas and the similar equations are used at outer layers. At outer layer, the maximum normal stress by substituting all these values in this equation will be equal to 1.116 megapascals, and the minimum normal stress will be equal to minus 14.866 megapascals. Similarly, the maximum shear stress can be obtained by using the equation tau maximum is equal to root of sigma AB by 2 whole square plus tau square, whose value is 7.991 megapascals. So this ends this numerical, but we need to ensure that the care has to be taken that the appropriate formulas has to be used, and this formulas has to be decided at the starting of the problem. The numerical has to be analyzed very much carefully. Unless we don't analyze the numerical, we should not further proceed to solve the numerical. Thank you for watching this video. Keep watching this videos, keep practicing the numericals so that you will be very good in solving the numericals, especially in design of machine elements. We will meet in the next video session. Till then, have a nice day.